It's the thing that says I can't talk to your parents about your grades and things like that.
Really? Huh.
Not without you specifically asking me to talk about them, and they just happen to be there.
Hey, Dr. Fox.
Yes.
The other day, yesterday, you were talking about how you typically don't like to do tests after a break. What is that? Do you feel like students perform less well?
I felt I performed worse.
Oh.
That when I was at Duke, my senior year, they had a week off for spring break. For Thanksgiving break.
Mm-hmm.
Then we had a week of classes and then exams.
Oh, wow.
And to me, that just sort of disrupted the whole flow.
Yeah.
Mhm.
That I would much rather have kept going to school the week of Thanksgiving and then just gotten out a week earlier at Christmas. So I projected that upon my students.
Do you feel like it would be better preparation for us if we took the quiz the day before the test
Instead of splitting it like how we.
instead of before spring break? That way it's more, I don't know, what do you think?
My gut says no, but there's also, and I know I'm not great at this part, but if we take it before the break, then I have a chance to grade it and give feedback in time for the test. And although that is my intent, it doesn't always work out that way. Matter of fact, often doesn't.
Should flip a coin.
Yeah.
Oh, there's a line.
Because I'm not gonna be here next week. I think
Neither
at all.
is,
Ashley.
yeah, she's not gonna be here at all, even on Tuesday.
Snubby-ness.
Yeah, that, y'all just decided you're too good for physics class.
Never.
Well, I think we need to give it a test then.
I dream about physics all the time.
Yeah, everyone should.
Mhm.
Any preference? I mean, you have your own style.
I mean, having the refresher before we take the test.
Yeah.
Okay, so
Would be
let's
good.
move it to the day before then.
Mhm.
All right, so the quiz the day before the test.
Mhm.
I guess, yeah, because that's what we were originally gonna do before we realized it was, right?
Yeah.
Break, before we realized
Yeah.
it wasn't.
Abby, did you want to weigh in?
I agree.
I concur.
So we're for flipping a coin.
Well,
All right, so
we did it in spirit. And won.
There we go, yeah. That makes more sense. I like that you put snow in quotations.
It was theoretical.
This is the theoretical stuff, not our experimental stuff.
I think in both days, it hadn't actually started snowing by the time we were
Mm-mm.
done with class.
Yeah, we
Before
would've.
I ever saw a flake in the air. All right, any questions related to, presumably physics?
Mm-mm.
Okay. So, I have a current running through a wire. I have a magnetic field running across this way. Uniform magnetic field. Now, what are the forces like on the wire?
This is. Wait.
All right, I have a rectangle of wire, and we'll just go ahead and put some dimensions on it. Since I'm using the magnetic field, how about X and Y? So I have an X by Y length of, or rectangle of wire through which a current is flowing. It is exposed to a magnetic field, which is running along the board, I guess perpendicular to the area of the square of wire. Area vector being out or in. What is happening? What are the forces acting on the wire? Just in case you think the top wire is not exposed, the whole wire is bathed in this magnetic field.
So only the areas where the magnetic field, only the areas where the magnetic field is the same overlapping. So if it's in the opposite directions, they cancel out.
Okay.
So that would, I'm trying to relate it to what we talked about.
There are multiple approaches, and this is completely valid.
Okay.
So if you think about what is the magnetic field created by the current, independent of the external magnetic field, then we can apply what you're going for.
Okay.
So what can you tell me about the magnetic fields created by the wire?
They are, it's going
It's coming.
out of the board in the center.
Mm-hmm.
Okay, so we have a current flowing around like that, so it's out of the board in the center, and what about on the outside? I think you said it.
Into the board?
Yes. Or using the right-hand rule for the current itself, so I have a current flowing down that way, so it's going into the board there, out of the board there. So I have this magnetic field into the board, out of the board, and then the same. Now, Laura was talking about sort of where the magnetic fields are opposing each other. Where are the magnetic fields opposing each other? Because we have this magnetic field, external magnetic field in green, and then we have the blue magnetic field coming from the current itself.
Technically, they're perpendicular instead of, like, the magnetic field going this way is perpendicular to, like, if this is a K hat, it's in the I hat direction. So I guess it's-
Just for the sake of language, let's go ahead and define that. Go for the brainwashed I hat, J hat, K hat. All right. So remember that the blue magnetic field, that which is coming from the current, is circular about the wire.
Right. So all of the, like, directly above the wire is when it is technically parallel.
Above the wire as in here or here,
Like, if this is one length of the wire
right?
and it's coming into and out of, right above where it would go, like
Okay,
this.
so the current's going like that, it's going, all right, so over here.
Yeah.
All right, so in this region right here, in front of the board, at least for this wire right here, So if it is going, so it's coming out and in, so if in front of the board, it's going that way, and behind the board, it's going with the magnetic field, which way will that part of the wire be forced? You were doing the hand gestures, right?
Follow along.
All right,
Out.
take your handy dandy, so I can free up a hand. All right, so let this represent that section of wire. The current is flowing down this, so my magnetic field is flowing around like that. We have that external magnetic field that is flowing that way. So where is the so we then I asked, where are the magnetic fields, I guess, going opposite each other? And that would be, well, since the external magnetic field is going that way, this magnetic field is going around like that, here, in front of it from your point of view. In front of it, it is, the magnetic field from the current is opposite direction of that external magnetic field. So the question is, which way will this part of the wire be forced?
It would be pushed. Yeah, would it not be pushed in that direction?
So,
Where there's
towards
no.
you?
Mhm.
Yeah, it would. So the force on that wire, and we have another color just for that, the usual. There we go. So the force on this wire is out at us. I make it look like it's at a single point, it's along the whole wire. I haven't done the stent gun yet. Have I? Stent gun, I think World War II British commandos, well, commandos I think are British anyway, but it's a gun that's got the magazine cartridge off to the side. Okay, you can picture it.
Sure.
I don't know if anyone else can. So the Sten gun, bullets come out the barrel. Well, that'd be the direction of the current, the positive charge. The magnetic field, it's got the multiple lines. You rarely draw a magnetic field with just a single line. Got the magnetic field coming from multiple lines, that's gonna be these. So bullet current comes out here, magnetic field lines come out here. So if my current's going down, the magnetic field's going off to, like, your right, my thumb points in the direction of the force. So current down, magnetic field's off to the right, thumb points outwards. The trigger, the thing that forces the whole thing, or the hammer.
Mhm.
The part that smacks into the back of the bullet.
Mhm.
Now, the book does a slightly different method of the right-hand rule for that, and that's fine, you end up with the same answer, just, I remember this better than the books. So, out. What about over here?
In.
All right, using the Sten gun, yep, there we go. We got a couple Sten guns going. No, that way. Magnetic field,
Mm.
current, force. Or the other method is the magnetic field from this. So here the current's going up, it creates a magnetic field around like that. The magnetic field from the current is opposite the magnetic field, external magnetic field on this side. So it will be forced inward. Oh, not a dot. What about on the sides?
Will it just be pushed in the direction of the magnetic field? Since the
Alright, so
Uh,
if we're doing.
the
well,
magnetic
whichever method
field
you use.
of our current is perpendicular to the magnetic field acting on the wire. So would they even
Wait,
interact?
sorry, start that one again.
The magnetic field from the wire on top or on the bottom
Okay, from
is
top.
perpendicular to the magnetic field acting on the wire.
Right?
And so none of them are against in opposite directions.
Therefore,
They'll just be moved in the direction of the magnetic field. Therefore nothing happens?
there is no force on top and bottom.
Okay.
Or if there is, they're gonna cancel each other out. Strike that last comment. So, yeah, nothing's gonna happen. So the force is just on those two wires. So I now have this square of wire being forced on the right-hand side, left-hand side, and pulled, so out towards you on this side, and this way on this side. So what's going on?
Is it spinning?
So, what do we call an influence that causes rotational motion? Or that might cause rotational acceleration? Flashback time.
Yeah, oh crap.
Hint, you could also say G2 Kumbuka as the answer.
Torque.
Thank you.
What?
You've forgotten
You
G2.
don't remember?
I don't know.
Hey.
This is back.
So anyway, I think I showed the video to one group to explain what it was, but I don't know if I showed it to any other group. All right, so we got a torque going on here. What is torque? Pardon?
It makes, well.
Oh, sorry. Give me a math formula for torque.
Sure.
Is this? It's got the moment arm in
Say it again, Stephanie.
it. It's got the moment arm in it.
It does have a moment arm in it.
Also the symbols in it for things that are similar to, for working with torque. Are different. Things that are function. Aren't the symbols IR?
No.
So,
it would IR would
I see an
be-
I.
that's IR, that's voltage.
So-
Depends on what you're representing, what R and I represent, but. What was that?
I something. It's like a little
Fish?
fishy thing.
Alpha.
Vector.
Okay,
Oh.
so we've got two different things going on here. So there is the formula tau equals I alpha. This is the Newton's second law with rotational motion. This is the F equals ma of the rotational world. In this case right here, this would be the total torque.
Is it the one that has force?
It does,
But it's.
force and moment arm. So this is the total torque. The other one is for an individual torque. I was hoping this would be
Oh.
a test of bringing stuff back for you
So-
instead of read my mind.
In my notes, I'm looking at my notes and I see an R vector cross product F.
Yeah.
There we go. R is the moment arm, F is the force. Cross product in the fact that the torque is gonna be perpendicular to the moment arm and the force. And if you recall, the direction of torque, right hand rule. So if I push the door closed, I'd get on the other side of the door, there's more than one way of doing it, other side of the door, and I push. So the force I apply is this way, the moment arm is that way from the hinge to where the force is applied, so that's my R, that's my F. R cross F gives me a torque upwards, which means it's gonna cause angular acceleration for the door to swing this way. I got some looks of recognition and remembrance and other looks of what? Well, hopefully it'll become clearer. So in this particular case, if I've got my wire right there, we need a moment arm, so we need to figure out where's my axis of rotation. So if I'm pushing on this side over here and pulling on this side over here, where's the axis of rotation? So it will rotate. Gee, that's what I just said. How about that? So what I wanted to look at is the total torque acting on this. So the total torque is going to be, we'll just do R right cross F right plus R left cross F left. And going ahead, we'll call it FR for right and FL for left. So total torque is just atomic torque. R right is a vector from the axis of rotation to where the force is applied, so R right, that's my R right, and R left would be this.